Hello and welcome to this edition of 30 Mechanical Minutes, virtual content for real-time professionals. My name is Doug Picklick. I'm the editor of HPAC Magazine, and I'm joined today by regular HPAC writer and well-recognized hydronics industry expert, John Siegenthaler. Hi, John.
Hiya, how you doing, Doug?
Very good.
Glad to be here.
Nice to see you this afternoon. Our subject matter today is all about staple-up radiant floor heating systems. And more specifically, we'll talk about the effect of heat transfer plates on the performance of these systems. First, I would like to acknowledge Rayhow, our sponsor for this episode of 30 Mechanical Minutes. Thank you very much for your support. So, although we only have 30 minutes today, we'd like to give our live audience the chance to ask any questions you may have. So for those of you with us today, you can click on the Q&A icon at the bottom of your screens. You'll also see a chat icon down there, but please put your questions into the Q&A tab so we're sure to see it. Okay, John, we're talking about staple-up radiant floor heating systems. But maybe let's back up a little and you can share with us just exactly what is a staple-up radiant heating system?
Yeah, well, actually, we're going to look at a couple different things. Staple up can mean different things to different people. You know, I put it down here in the form of a question. What's a staple up floor heating system? Well, it's tubing and then possibly plates that are stapled to the underside of a wood subfloor. And within that, there's several different variations. We can have stamped aluminum plates. We could have extruded aluminum plates. We can certainly have different types of tubing. And I put down "and plates" in question mark for a reason. There is such a thing as a plateless staple up. And right at the get-go, I'm going to really urge you to avoid plateless staple ups. They are very, very inhibited in terms of performance. I've had over the years many callbacks, inquiries. We've actually never done a plateless staple-up system in our design work, but I've had many inquiries that ultimately are traced back to the lack of plates or lack of proper underside insulation on these types of systems. So I want to stress the plates are really important, and I'll build a case as we go through today. Also, I want to refer to another term, what I call a tube and plate floor heating system. And again, by its name, there's tubing there. Certainly, it could be PEX or PEX aluminum PEX. And the plates are an integral part of the system. And they can be installed, the tubing and the plates can be installed either below the floor or above the floor. And down at the bottom there, you'll see a couple construction details. Over on the left side, that's an underfloor tube and plate system. It shows, in this case, stamped aluminum plates that today are either 5 or 6 inches wide. You'll see the tubing goes into a groove there in the plate. Those are stapled directly to the bottom of the subfloor. And then underneath there is nominal 6 inches of fiberglass insulation. And that's assuming that the space under the floor is conditioned space. If that were unheated space, like an unheated crawl space, you'd probably want to go to at least an R30 product, or certainly whatever the code minimum is on that. And you can see you can do a variety of floor coverings on top. It could be glued down wood flooring, could be ceramic tile with a backer board under it, or it could be a low pile carpet. Over on the right side, it shows another approach. This is an above floor tube and plate. So the same tubing, the same plates are shown installed above the floor. And you'll see there that there are plywood strips, we call them sleepers, that are put down. And basically what the plywood strips do is they create a substrate with grooves in it so that the groove where the tube is located in the plate actually has a place to recess into the floor. And once the tubing is in place and it's pressure tested, again, there's a variety of floor coverings you can put over that. Now, again, I'm showing these as stamped aluminum plates. I will mention Rayhow actually makes a really nice product, ROW panel, that is an extruded plate that is designed for an above floor application. Basically, it eliminates the need for these wide plywood sleepers that you see here. So those are a couple variations on this concept of tube and plate. So Doug, let's go to the next slide. Yeah, so let's, again, here's some photos that show an above floor tube and plate system. Again, this was done with the thinner stamped aluminum plates, same construction detail. Actually, over there on the right-hand side, that photo shows, you can see the plates. They're installed 8 inches on center. That white tubing is actually 1/2-inch PEX aluminum PEX. And I do want to give you a personal preference here too. I really do like PEX aluminum PEX on any system using aluminum plates. And the reason for that is that the aluminum core in that tube is going to have an expansion coefficient that's roughly the same as the plates. We don't get a lot of differential movement between the tubing and the plates as they change temperature when we have a PEX aluminum PEX tube there. These systems have been done with standard PEX tubing. It can work, but you realize that a standard PEX tube expands about 10 times as much as an aluminum plate for the same temperature change. So it's going to set up the possibility of more expansion, contraction, what we call ticking sounds. So to minimize those, we like to work with a PEX aluminum PEX product, regardless of what type of aluminum plate we're using. And then you can see in that photo also the 2 holes through the subfloor. They're actually drilled at a fairly shallow angle, and the tubing basically just dives right down through the subfloor at that point. And in this case, the manifolding would be down in the basement. And that's fine. The manifolds do not have to be above the level of the tubing. With good forced water purging, you can displace the air and not have a problem. The 2 photos in the bottom there, that shows the plates being stapled down. And I'll mention another detail that's important here. When you fasten a plate on a floor like that, you only want to staple one side of the plate. You want to leave the other side of the plate unstapled so that as the plate heats up, as you're putting the tubing into the plate can expand just a little bit to accommodate that tubing. If you staple both sides of the plate down, you may have a difficult time getting the tubing to drop into the groove. And I should state the wrap of the aluminum plate around the tube is a little more than 180 degrees. So it's designed to actually capture the tube and hold it in place once it's pressed down into that groove. So again, only staple one side of the aluminum plates when you're putting that in. And again, you'll see the underside insulation detail, really important.
Now this is a hardwood floor installation.
It is, yep.
When they tack that in, I mean, often they're driving nails through there, so they obviously they need to have some caution. You definitely want to make sure you can see where the tubing is. And if you look at where he's using that nailer, he's actually halfway in between those plates. So he's actually nailing right into the plywood, not having to pierce down through the plate. And that would be the case on the photo over on the right too. As you put the flooring down, you can see right where the plywood is, where the tubing is. Where you want to be really careful is where those return bends are, because now the tubing is actually going to start, moving to a different position relative to where you've been nailing. So basically, you just want to keep track of where that tubing is. It's okay to shoot a nail down through the aluminum plate. They're only about 20 thousandths of an inch thick. Obviously, do not want to shoot a nail down through the tubing. So good point. Okay. Well, we're here today to talk about some of the best practices when it comes to installing these systems. And you sent me some photos of some good and some maybe not so good staple up examples. So well, let's look at something done correctly.
Yeah. So here we are. We're back below the floor now. So we're in a below floor tube and plate, or what is often referred to as a staple up system. And the tubing here is 8 inches on center. That floor framing is 24 inches on center. So it coordinates well with either 16-inch or 24-inch framing. And you'll see the plates that are up there. You'll see that there's been quite a few staples. We want those plates tight against that subfloor. We don't want gaps there. We don't want air between the plate and the subfloor. You also see that the plates have a very well-defined groove for the tubing. These are not plates that were hammered together on site. They are precisely formed to fit the OD of that tubing. And again, after a system like this is installed, it's going to be pressure tested to make sure there are no leaks. And then 6 inches of fiberglass is going to be pushed all the way up to the underside of these plates. Several years ago, there was a question on that, whether the insulation should go all the way up against the plates or not, especially if it had an aluminum facing. There was some research done on that down here in the States. And actually, the better performance was obtained when the insulation was pushed all the way up. So push the bat right up tight against the bottom of the plates. And you're probably going to have some kind of a covering on the bottom. You don't want to leave just a raw fiberglass surface exposed to the basement. So either craft paper or Tyvek or something underneath there, because over time, you're going to get small little pieces of glass fiber that could break off of that bat. And rather than have that kind of dust down on the space below, you put a covering up there. So again, that's a good installation that, depending on the floor covering, that would be compatible with ModCon boilers or water-to-water geothermal heat pumps or air-to-water heat pumps, probably requiring a design load temperature in the range of maybe 120 degrees Fahrenheit.
That surface being carpet, ceramic tile, wood flooring, does that make a significant difference?
Sure does. I would tell you, with a system like this, to limit the total resistance on top of that plywood to R1. Remember, you have the resistance of the plywood floor itself, which is close to R1 in and of itself. So on top of that, nothing more than an R1 resistance. And all of those systems that I'm showing are possible. But carpet, to do that, you don't want to pad under the carpet. Typically, it would be glued down to that subfloor. And the wood flooring typically is going to be an engineered wood product, a thinner product, maybe ½ an inch thick, probably put down with a mastic, a full bed of mastic underneath to bond it down to the floor. And again, what we're trying to do, we're trying to eliminate air between the subfloor and the finished floor. We're trying to eliminate air between the plates and the underside of the subfloor. So we're counting on conduction, heat transfer, to move heat from the water in the tube, basically through all these different components and ultimately up into the room.
Okay. So what can you tell us about these jobs here?
Well, Doug, I could actually spend a whole afternoon showing you pictures of poorly done, quote unquote, staple ups. And I think the one in the upper left kind of speaks for itself to some extent. The plates that are there are not manufactured plates. In my opinion, somebody went out and bought a coil stock, probably for roof flashing, and just hammered out some kind of shapes out of that. And you can see the bond between the outside of the tube and the plate is really poor. And that air and that lack of contact between the tube and the plate is going to severely affect the heat output of that floor. So that is really a poor job. Down below it, you'll see what looks to be a neater installation. But here we've got ½ inch PEX tubing that's stapled to the side of those eye joists. And again, no plates, no insulation, really challenging thing. We look at systems like this and we use a term, we say that these systems are thermally constipated. And by that, we mean we can put the heat into the tubing from whatever our heat source is, but that tubing is going to struggle to transfer that heat to where it's supposed to go above the floor. Over on the right are just some more examples where somebody stapled the tubing or clipped the tubing. The one in the upper right, they've actually clipped it to the side of floor trusses. The other two, it's clipped or stapled to the bottom of the subfloor. This tubing, folks, there's nothing magical about it. It's plastic pipe. You can't treat this the way Chevy Chase staples his Christmas lights in the movie Christmas Vacation. So these are all bad examples. So stay away from this, and your phone will not have as many troubleshooting calls.
Okay, and then so you do have best practice design, basically, ideas for installing these systems?
Yeah, these are some more details. If you are going under the floor, in the middle there at the top, you want to make sure that the holes that you're drilling through your floor framing, where you're going to route this tubing through, you want to keep them down at least a couple inches to make sure nobody drives nails from the top and hits these tubes. Over on the far right, I'm just showing the sequence of how you would pull tubing. Basically, you pull it and you thread it through these holes until you get to the farthest joist bay, and then you work your way back. And I want folks to take a look at the curvature of the tubing, especially on the left side there. You notice there's no really tight bends in this tubing. We don't want to crimp the tubing or pinch the tubing where it comes out of the plate. Ideally, it should be pretty close to straight where it comes out of the plate. And then the photo in the bottom, one of the things that I recently saw in a project is where the installer had done a lot of things very right. You can see the plates are 8 inches on center. They've been very careful to snap lines, keep everything nice and straight. But the return bends were right out just inside of that band joist. Okay. Now, that was going to get spray foam insulation against the band joist. And if that tube is either touching the band joist, or if it's only in maybe half an inch or 1 inch away from the band joist, that's a potential freezing location. Just imagine when it's very cold outside and perhaps you're going into a temperature setback in the house, there's no flow in this tube for several hours. You could freeze the tubing up because basically you don't have good insulation between where the tubing is and where the band joist is. The band joist itself really doesn't provide much R value. Fortunately here, this was PEX aluminum PEX tubing. It was just bent down carefully by hand to get the return bends about 4 or 5 inches in from the inside surface of the band joist. And that allowed space to put the entire thickness of spray foam and still keep the tubing on the inside. So again, it's a small, easy to miss detail, but I stress to you, make sure that your tubing stays completely within that thermal envelope of that building.
Right. Okay.
Okay.
Now, we really wanted to talk about the benefits of using heat transfer plates on staple up as opposed to going plateless. So you sent this one as well.
Yeah. What this is, Doug, is it's based on a computer simulation. And what I did is I set up a cross section of a floor similar to what we've been looking at for below floor tube and plate, where we've got 3/8 ceramic tile as our finished floor. We've got a 3/4 inch plywood subfloor. We've got the plates, and you can see the tubing there with the white circles. And if you look carefully, you'll see the white lines that represent these plates. They're 6 inch wide, 20 thousandths of an inch thick stamped aluminum plates. And then down below the plates, I'm showing 4 inches of fiberglass. And the colors that you see there, the reds transitioning ultimately to the blues, that shows you what these heat transfer plates actually do. I think there are misunderstandings in the industry. I've heard them called reflector plates before, and they are shiny, but the purpose is not to reflect. The purpose of these plates is like a wick. Think of it as a wick for BTUs. What we're trying to do is pull heat from the tube and spread it out across the floor. Ideally, we would have very little variation in surface temperature across the floor. And of course, if we went with wider plates, we could reduce that. But if you compare that middle graphic there, where you see the wide red spots, to the one at the bottom, all I did for the one at the bottom is take away the plates. None of the other materials changed. And again, I use this term thermal constipation. You can see that there's temperature gradients around the tube, but they're definitely not spreading out to the extent that they did with the plates. And then the graph up at the top, those are plots of surface temperatures, both with the plates and without the plates, and for two different water temperatures. And the characteristic that you see with the plates is you get these plateaus with a little dip in the middle where there is no aluminum. But that is a much better surface temperature profile compared to what you see without the plates. Without the plates, you tend to get these peaks, very defined peaks right over the top of the tube. And this is called striping. And if you push the water temperatures up, because without the plates, you're not going to have very good heat transfer. So the common, installer correction is bring up the water temperature. If you're working with a boiler, for example. Well, you can do that and you can get more output. The problem is you're severely stressing the finished floor as well as the plywood. Plywood really isn't supposed to operate above about 140 degrees Fahrenheit. There's actually a loss of strength that's documented as you get into very, very high temperatures with plywood. You're not at a temperature where you're going to combust anything, but there is definitely a loss of strength, potential outgassing of some of the adhesives that are used. And one of the things that I have seen with very high temperature striping is with a vinyl floor, you'll actually get a discoloration of the floor directly above the tubes, which, to me looks kind of cool. You can see exactly where your tubing is. So if you do a nice, neat tubing layout, it basically over time kind of shows itself up above. But that's me. Most consumers are not going to tolerate that. So don't do that. Don't install a system without the plates. In round numbers, folks, you will get about 3 times the heat output if you use the plates the way they're shown here compared to a plateless system. So think 30 BTUs per hour per square foot rather than 10 BTUs per hour per square foot where you omit the plates or maintain that ratio. Again, you do not see this in other markets. You will not see plateless staple up in the European market or the Asian market. I'm not sure how it evolved in the North American market. Somebody probably said, well, you can reduce the price of this project by leaving out the plates. And my counter argument is, my background was actually aeronautical engineering. And very early, I figured out how you could save a lot of money building airplanes. And you just leave the left wing off. And it guarantees that the plane will be substantially less expensive. And Doug, I did hear you snicker a little bit there. And it's meant to be kind of a sarcastic joke. If you want these systems to work, especially with modern heat sources like heat pumps, it is important that you maximize the lateral heat dispersion and use these plates.
Okay. I was also going to ask, John, does the formation or the gauge of the metal, the aluminum, make a difference?
It actually does, but there are both stamped aluminum plates, what I'll call the thin plates, and there are several products on the market now that are extruded plates. One of the things that we also did with computer simulation is we modeled the thin plate first, 20 thousandths of an inch thick, 6 inches wide, and we calculated how much metal is in a plate like that. And then we just kind of made a hypothesis. And the hypothesis was if we use the same amount of metal, but make the plate half as wide and twice as thick, which is going to perform better? So we didn't necessarily model any specific product in the market, but we did say for a given amount of aluminum, are you better to spread it out in a thinner plate or to keep it more narrow with a thicker plate? And actually the thinner plates did do the higher performance by about 20%. Now, that being said, remember, these models assume that you've got good contact between the materials, that you don't have air gaps in there. And for a given width, the thicker plate will perform better. it actually comes down to in heat transfer something called fin efficiency. And as an example, the fin efficiency of the thin plate might be, let's say 97% of what is theoretically possible. If you double the thickness of the plate, the fin efficiency might go from 97 to 99% of what is theoretically possible. So yes, thicker fins will give you better lateral heat dispersion, but the gain is very minimal in terms of comparing it to the cost of the material, the extra material. So I would tell you either system, the extruded plate system or the stamp plate system can work. Just follow the installation details. I prefer, again, PEX aluminum PEX tubing for reasons of coefficient of expansion. And I also prefer 8 inches on center. It coordinates well with framing, and it builds a floor heating system that not only is compatible with perhaps a ModCon boiler today, but 10 years from now, 15 years from now, that ModCon boiler might be replaced by a heat pump. And we don't want to have to go back and make substantial modifications on our original system. We want to future-proof it. That's kind of the concept. So I would suggest 8 inches on center is a really good spacing to work with today that future-proofs your system for tomorrow.
Okay.
Excuse me.
We are going to jump to our questions. We've got a few here. I'm going to start with this one from Bernie. He's asking, can you also cover tube and plate ceiling systems, especially below the ceiling plywood with covering? A good design, performance, etc. What do you?
Well, we don't have time to cover it, but I
Right.
can tell you the tube and plate systems absolutely can be used on not only ceilings, they can be used on walls as well. I think we've probably got some HPAC articles in the past that have shown that assembly. If not, maybe we'll schedule one for the future. But yes, the tube and plate system can work for ceilings as well as for walls. And both of those are actually underutilized strategies today in the overall hydronics market. You know, you run into a project where somebody wants thick carpet. Radiant ceilings are ideal in that situation. Radiant walls can be used in places like you can actually do a radiant wall in a walk-in shower. You could do it in a Cape Cod style house where you have knee walls. So if you've never done a radiant wall or radiant ceiling, I would encourage you to take a look at some of the material that's out there on how to do that. It's another tool in your toolbox for hydronic design.
Right. Okay, we've got Dale has asked, or well, states, I heard that it is better to screw the plates to the bottom of the subfloor over the staple method. Do you hear about stapled plates dropping off in time? I've been to job sites where this has happened.
I won't say it's impossible, but I'd question what kind of staples are being used. These are not staples that you would drive with just a standard, you know, spring action Bostitch staple gun. These are probably electric or pneumatic staples. I would say to use a staple that's probably at least a 5/8 inch long staple. And to be honest with you, we have never had a problem with the plates coming loose. Just made me think, again, I've mentioned the use of PEX aluminum PEX tubing with aluminum plates reduces any differential expansion between the tube and the plate. That job where those plates came loose, part of the reason, and I'm speculating, but part of the reason might have been the movement of the PEX tubing back and forth, you know, hundreds or thousands of times over the years, potentially stressing those staples. But again, we have not seen that as a problem. So proper staples with either an electric staple gun or a pneumatic staple gun, make sure you're, you know, getting them in. I have no problem with screws. Screws are going to be quite a bit more time consuming, and they're probably going to be more expensive, but I have no problem as long as you keep the plate flat and make sure it's, you know, tight up against the subfloor. Screws would be fine.
Okay. We've got two more questions. Bob, here's what Bob says. I always have the question of where is the best place for a floor sensor in these installs, above or below?
Ooh. It's a good question, Bob. I'm not sure. We've actually not used floor sensors in these systems. The problem or the difficulty in thinking through this, I mean, you're going to have a range of temperatures depending on where you put the sensor, not only above or below, but how close to the tube. Is it next to the aluminum plate? Is it between the aluminum plates? I'm not sure. I guess if I had to just arbitrarily pick something, I'd probably say halfway between the plates or between the tubes, maybe right in the plywood. And then you would have to adjust the controller based on at that location, it's not going to be as hot as it would be, for example, where the tubes are. Yeah. So again, I don't have experience to give you an absolute best practice there.
Okay. Our final question for today from Sean: can the plates be used in a cement slab install?
I would hesitate on that because, first of all, aluminum and concrete don't always get along very good. The aluminum can be corroded with concrete around it, depending on what's in the concrete. If there's any kind of salts in there and so forth, that will tend to corrode the aluminum. And I'm not sure if you would get much of a performance increase, especially against the labor involved. The only way I could imagine you doing that would be to have the tubing and the plates at the bottom of the slab and pouring a slab over the top. I can't imagine how you would pour a slab where the plate is suspended within the thickness of the slab and still get the concrete under the plate and not destroy the plate in the process. And remember that in a slab, and this is actually a good lead into our next 30 mechanical minutes. We're going to be talking about where the tubing is best located height-wise within the slab. And I'll give you a hint. It's not at the bottom of the slab. So that's actually probably a good segue into our next one, Doug.
Yeah, no, absolutely. So Sean, thank you for that question. Perfect timing. And thank you, John, again for participating in today's webinar. That's our 30 minutes, and we almost nailed the time right on. So thank you for that. And thank you to Ray Howe again for sponsoring this edition of 30 Mechanical Minutes. And of course, thank you to everyone who joined us on the webinar today. A recording of this session will be available on our website, hpacmag.com, in the days ahead. And as John mentioned, please keep on the lookout for our next 30 Mechanical Minutes sessions, including Wednesday, October 20th, when John will join us once again, this time to talk about the ideal tube depth for in-slab floor heating. So thank you again, John. Thank you, everybody. And until next time, thank you for joining us. We'll see you then.
Take care, folks.